All right, folks, this lesson's called matching models. We're going to match FBDs with VVTs and PVTs. Sounds complicated. It's not so bad. So let's take the skater. They're going to be moving in the horizontal position. So we're going to use X because X, that's the symbol for horizontal position measured in meters. If they were doing any ollies or anything like that, we'd give them a Y because Y is the symbol for vertical position. But this is kind of a beginner skateboarder and they're not doing any ollies or anything like that. Okay, so let's say that they're moving with a constant velocity and we've drawn their velocity vector like that. Is that a positive velocity or a negative velocity? It is a positive velocity, and that's because the sign, positive or negative, of the velocity tells you the direction. I want you to memorize that. The sign, positive or negative, of the velocity tells you the direction. Okay, if the skater wanted to slow down, meaning needing an acceleration, would that acceleration be positive or negative if this skater wants to slow down? Boom, that's right. They would need a negative acceleration. They would need a negative acceleration. And that's because if the velocity vector is pointed in the opposite direction of the acceleration vector, the object will slow down. So here's our velocity vector, positive, and our acceleration vector needs to be negative if this object is going to slow down. What if you have this new case where you have the velocity vector to the left and the acceleration vector also to the left? Are they going to speed up or are they going to slow down? If the velocity vector is pointed in the same direction as the acceleration vector, the object will speed up. So this is where students always mess up. They think, okay, so I got a negative acceleration, that means it's slowing down. No. A negative acceleration does not by itself mean the object is going to slow down. It has to do with how the acceleration and the velocity sort of work together. So I try to remember if they're going in the same direction versus if they're fighting each other, they're going to be slowing down. So how can he slow down? Well, this is no ordinary skater. It is Sir Isaac Newton. And Newton knows that an object will remain at a constant velocity unless acted upon by an external net force. A net force will cause an acceleration, either speeding up or slowing down. So Sir Isaac Newton, he needs a net external force. What is he going to do? There's several ways to slow yourself down or use forces. If you're a skateboarder, you could do a power slide or put your tail down. But this physicist skater, he drops his Vans, his sick Vans, and he brakes by putting his foot down. And now he has a net force, which is going to cause an acceleration. The cause is the net force. The effect is the acceleration. Okay, so now we want to draw the free body diagram. Before he's moving at a constant velocity, the forces are balanced. But what are these forces? What is this force in the up direction? And what is this force in the downward direction? What are they? There they are right there, written out. The skater is on planet Earth and therefore should feel a gravitational force. There it is, pulling him down. The skater feels the street pushing up on him with the normal force. This balances the force due to gravity or the weight. So we're learning how to draw free body diagrams. So what about after he puts his foot down? What would his free body diagram look like? Well, bam, that's what it looks like. So we have, when the skater puts his foot down, he feels a frictional force. Here's the frictional force. It is in this direction, slowing him down. He now has a net force. He now has the net force because of the unbalanced force of friction. See, there's no force over here balancing that force of friction. So now all this force over there, that's net, that's extra unbalanced force. So he is going to have that negative acceleration. Okay, which VVT graph matches? So here we have some VVT graphs, velocity on the y-axis, time on the x-axis, and we're going to recall that the skater had a positive velocity and a negative acceleration. So which one of these graphs show that we have a positive velocity and a negative acceleration? Just so you remember, Positive velocity, negative acceleration, and there's that free body diagram that'll help us match the velocity versus time graph. So which one is the correct answer? It's C. Why? Because you got to look at the y-axis. The y-axis shows us, look at all these positive velocities. That's showing us that he's always moving in the positive direction or to the right. Now, the slope of a velocity versus time graph is the acceleration. I want you to memorize that. As time is passing, the velocity is decreasing, so we have a negative rise. This is a negative slope. This is a negative slope. And if the slope is the acceleration, then we know we have a negative acceleration. And that's what matches our scenario. Okay, last one. Which position versus time graph matches? Again, I'm going to look at the axes. I see we have horizontal position shown on the y-axis, and we have time on the x-axis. And let's remember that the slope of a position versus time graph tells you the velocity. And let's remember that we know the velocity is positive, and we know the skater is going to be slowing down. So which one of these shows a positive velocity and slowing down, given that we know that the slope tells us the velocity? Boom! If you said B, you are correct. First of all, this is a First of all, this is a positive slope. The slope is positive. The change in position or rise is positive as time passes. Look, time is passing, and then our change in position is positive. That's a positive slope. The slope is decreasing or getting less steep. Look at how steep we are at the beginning of time. As time's passing, this almost becomes a slope of 0. And remember, if the slope is the velocity, then our slope is telling us, a 0 slope right here is telling us that we're going 0 meters per second. That is stopped. So we must have been slowing down. So a line that looks like that shows slowing down. That's it. That's it, folks. We've drawn free body diagrams. We've drawn velocity versus time graphs. And we've done position versus time graphs. We know physics. Good job, guys.